So let's finish up our review for the last regular chapter exam, which will be on Thursday. That gives us next week, Tuesday and Thursday, to review for the final. Okay. Number 34. Here we go. Which of the following has a bond order of 1.5? So we're looking for a bond order of 1.5 out of E. E means none of these. So we want O2 plus N2, O2 minus, and C2. All right. The oxygen is going to be one that does not have SP mixing. So it's going to be, let's see, let's count up the number of electrons first. We should have valence electrons only, so we don't have to deal with the first period. Would be 6. So 6 times 2 minus 1 for that positive. What's that, 11? 11 valence electrons. Nitrogen's going to be 10 electrons. This is going to be 12 plus 1, which would be 13 for that one. And then carbon would have 8. 2 times 4. Okay, now we can do the shorthand molecular orbital configuration. All right, so we're going to have a sigma from the 2s and a sigma star from the 2s. Then we'll have a sigma from the 2p, and then we'll have a pi from the 2p, and then a pi star from the 2p, and then a sigma star from the 2p, if we need that many. Okay, that's no SP mixing. If there had been mixing, then these would be swapped. And that's the case for nitrogen. So nitrogen's going to be like that, and like this, that. 2p, 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 2s, 2s. There we go. And I'm going to use this one to talk about that one. And carbon would have SP mixing. It's not going to need quite as many orbitals though. We're probably going to go like this, and like that. Okay, so for oxygen, we have 11 electrons, right? Sigmas can hold 2. So that's 4. Yeah, 7 more to go. 5 more to go. This can hold 4, and there's 1. Let's see, 2, 4, 6, 10, 11. That's right. Okay, what's the bond order of this one? It would be 2, 4, 8, right? 8. And then minus 3 divided by 2. And that's equal to 5 divided by 2 is 2.5. I did that right. This one, we've calculated that one so many times. That bond order is 3. Now, if we add 2 more electrons for this one, they would go here, wouldn't they? So this would be 3 for that one. Okay, so that means we still have the same number of bonding electrons. Now we have two more non-bonding or anti-bonding. So that's 1.5. There's our answer right there. If we try to calculate, this one would be 2, 2, and 4, right? So this bond order would be 0. Oh, excuse me. I didn't do that right, did I? I'm not thinking that. 6 minus 2 divided by 3. So that's 4/3. What am I talking about? 4 divided by 2 is 2, right? Okay. All right, so our answer is C. Right. 36. I'm gonna leave those up there temporarily, in case we need to. No. This is a heteronuclear example, so we got to start over again. Boron and nitrogen. Okay, so we have which of the following statements about the molecule Bn is false? Assume sp mixing. Okay, so if we do boron and nitrogen, since they're both in the same period, we should be able to use the shorthand method without having to draw out the diagram. If you get a molecule where you've got atoms coming from different periods, then you usually have to draw the energy diagram to figure out which ones are actually forming the molecular orbitals. But this one should be safe. And if we're assuming sp mixing, which makes sense, because boron and nitrogen are both on the left-hand side of that dividing line, then we would start with 2s and sigma star 2s. Then with mixing, we would have pi 2p and sigma 2p, then pi star 2p and sigma stars. Boron is contributing 3 electrons, nitrogen contributing 5, so we have 8 electrons, 8 valence electrons. So that's 2, 4, and 4. That's it. Okay. Now what's the question? Oh, we have several different statements that have to be considered. All right. It's paramagnetic. All right. Remember the difference between paramagnetic and diamagnetic. Magnetic. Okay. Para means alongside or with. So these are the ones that are drawn into the magnetic field. And dia means opposed to. So we've got paired electrons here. We've got paired electrons here. 2, 4. All paired. So this would be diamagnetic. That means A is false. Its bond order is 2. All right. Bond order will be calculated as 4 and 2 is 6 minus 2 divided by 2. And that's 4 divided by 2 is 2. That's true. B is true, I think. Wait a minute. Now, why does it say the answer is A? It's paramagnetic. Unless I drew this wrong.
It's asking for the false.
Oh, which one's false? Oh, okay. I could have had a V8. The total number, okay, all of these are true. Well, they can't be because we found a false one. So C and D should be true. Total number of electrons is 12. Total number is 12. These are valence electrons. And then you have a 1s sigma and sigma star. So that's plus 4 equals 12. That's true. Total number of electrons. And then has 2 pi bonds. Has 2 pi bonds. Now that's false. Right? Because a bond order of 2 means a sigma and a pi. Unless that's what it means.
That's what it looks like.
Yeah, I think that's what they're getting at. It has this pi orbital filled and this pi orbital filled. We have to interpret it that way. Otherwise, there's no right answer in there. Okay. And that makes sense because at this point, we're trying to praise the value of molecular orbital theory over everything else. And you wouldn't know that with any other theory. 38. Okay, which of the following molecules or ions is not paramagnetic in its ground state? Not paramagnetic. So they're all paramagnetic except for one, which is diamagnetic. All right. So let's look at each one. This is O2, O2 plus, B2, and NO with no mixing, and E is F2. Okay. No mixing, no mixing, mixing, no mixing, no mixing. This is the only one that has mixing. All right, so the rest of them are going to be sigma 2s, sigma star 2s, sigma 2p, pi 2p, pi star 2p, and sigma star 2p. Okay, and this one with mixing is going to be star pi 2p. We probably need all those. I'm going to stop there. Okay, so valence electrons for oxygen would be 12 electrons. This is going to be -1, so that's 11. Boron has 6, 2 times 3. Nitrogen is 5, oxygen is 6, so that's 11. And fluorine has 14. 7 plus 7. Okay, so 12 would be 2, 4, 6, 10, 12. This is going to be paramagnetic because of this one right here. Unpaired electrons. Okay. This one is missing one. So it's going to be, where is it coming from? The highest orbital. This one's only got 1 in it. So it's also paramagnetic. Should be able to measure the difference between the two. This should be more strongly paramagnetic than that one. Let's see, SP mixing, 6, 2, 4, and 2 to 6. Yep. There we go again. This one's paramagnetic. And NO should be based upon this one up here. So with 11, it should come out the same as that one. Yeah, should come out the same with 11, 11 here, 11 here. This one should also be paramagnetic. Okay. And this one is 14. So it's going to be 2, 2, 2, 4, which is 6, 10, 4 more, and 4. This is diamagnetic. Because this pi star, which is the highest one, is completely filled. Yep. So that the last one, fluorine, difluorine, is diamagnetic. It's not paramagnetic in its ground state. Okay. Let's see. 39. Might as well just redraw it. I need to practice anyway. In the molecular orbital description, carbon monoxide, assume sp mixing. Okay, so we're saying that the carbon overwhelms the oxygen. In other words, as far as mixing goes. So we've got carbon monoxide. That means, and yeah, we do have to draw this. This is carbon is 4 and 6 is 10 electrons. So sigma, sigma star, 2s, 2s. Oops, mixing. Pi, 2p, sigma, 2p, pi star, 2p, sigma star, 2p. So with 10, you got 2, 4, and 8, and 9, 10. Okay. So everything's paired. That means carbon monoxide is diamagnetic. But let's see. Let's take them one at a time. A, B, C, D, E. So A says the highest energy electrons occupy anti-bonding orbitals. Well, that's false. Right? Yeah. That was false. The highest level is a bonding orbital. B, 6 molecular orbitals contain electrons. Well, okay. 1s and sigma are 1s. So these would be filled also. 2, let's see. 6 molecular orbitals. 1, 2, 3, 4, 5, 6. Well, that's true. 6 molecular orbitals contain electrons. B is true. Right? Am I reading that right? Molecular orbital description. 6 molecular orbitals contain electrons. Yeah. The way I read it, B is true. Okay. C, there are 2 unpaired electrons. No, there are no unpaired electrons. D, the bond order is 3. All right. If we use the complete structure, we have 2, 4, 8, 9, 10, minus 2, 4. What about 2? Yeah, that's 3. D is true. All the above are false. That's false. Okay, so we got a mess here.
6 molecular orbitals contain electrons.
6 molecular, oh, wait a minute. No, that's false. Here's why. Pi orbitals, pi's have 2 orbitals in them. All right, so it actually has 1, 2, 3, 4, 5, 6, 7.
Okay. Now I know why it says that's false.
Yeah, that's right. All right.
Press one
Yes.
on our answer sheet.
Uh-huh.
It in our question 39, it says you have 5 molecular orbitals instead of 6.
Oh, that's because I wasn't counting the 1s orbitals.
Okay.
I probably should correct that. So if you're thinking of totals, I mean, you have to consider all of them.
Yeah.
Let's see. 41. Which of the following statements about the carbonate ion is false?
Carbonate. Oops. That's 3. With a 2 minus charge. The carbonate ion is false. B, C, E.
All right, orbitals on the carbon atom are sp2 hybridized.
Well, let's see. We've got 4. 3 times 6 is 18 plus 2 more. So that's 24 electrons. We've got a carbon and 3 oxygens. So that's minus 6 is 18. 2, 4, 6, 8, 10, 12, 14, 16, 18. All right, all used up. It says 2 minus charge. And we would have to resonate with 3 possible Lewis structures. One of them would be that. The other one would have a double here and the other would have a double there.
But there are only 3 groups around that carbon. So that's S and 2 P's, sp2. So A is true.
A is true. It is sp2 hybridized.
Right, under the valence bond theory. B, the ion is expected to be diamagnetic.
Okay. So we've got to draw out the carbon and oxygen. All right, should we have mixing?
Carbon monoxide had mixing with carbon and oxygen.
But here we have 3 oxygens. So I'm gonna propose that there's no mixing.
Because it's 3 against 1.
Okay, so we would have sigma from 2s, sigma star. It may not matter. Then 2p, pi, 2p, and then pi star, 2p, sigma star, 2p. I don't even know if this is going to work. Because when you got 3 oxygens in there, each one is contributing an S, a 2s, and a 2p. And if we count up all the electrons, we've got 24 of them. 2, 4, 6, 10, 14, 16. Right? We still got electrons to use. So
That shows my deficiency in understanding molecular orbital theory for more complex molecules. The ion is expected to be diamagnetic. What kind of explanation did I give in here?
The only thing we have is there are no unpaired electrons.
Oh, okay.
You didn't give no like explanation.
Yeah, I didn't draw it out, probably because I couldn't. Yeah, my expertise doesn't go that high. Yeah, I don't have an explanation. So, this one would have to be true. Right? Expected to be diamagnetic. That makes it a bad question, doesn't it? Yeah, it does. CO bonds are different lengths. No. CO bonds are all the same length. So C is your false one. Total of 24 electrons. Yep, that's true. And the last one, all the above are true. That's false. So C is false and E is false. So take your pick. That's a bad question. C should be, yeah, that's right. They're not different lengths. They're actually the same lengths. You might expect them to be different lengths, but they're not. They're actually the same length. Whoa. Do something about that. Maybe that's why I stuck it in here, because it was messed up. Be sure not to miss it. Uh, 42. Or as an illustration of real life. Murphy's Law. How many electrons are involved in pi bonding in benzene? All right. Okay, so you've got a sigma bond between each one of those carbons. And then sometimes we write it like this, that, and that. Other times we write it like this to show that they're delocalized electrons. But how many electrons, you can't tell from this, but this does tell you. You've got 2 electrons here, 2 here, and 2 here. So 6 electrons are just delocalized in that pi bonding system, in that aromatic system. All right, number 45. See if somebody snuck in while I wasn't watching. Wyatt. No. Allison. And the other Kaylee. Okay, 45. Which of the following has the highest bond dissociation energy? Okay. Well, we know, and the bond dissociation energy is how much energy is required to break that molecule into 2 separate atoms, right? So if we work from this one, we know that that one's going to be a bond order of 3. But let's, they're all dinitrogens. So let's just draw one system out here. One molecular orbital system. And this is mixing. And single star. Okay. So this one has 10 electrons, right? And let's just put the rest of them up there. N2 minus has 11 electrons. N2 2 minus, 2 minus has 12 electrons. N2 plus
as 9 electrons. And into 2 plus as 8 electrons. Okay. If we start with this one, 2, 4, 8, and 10. Okay. So this gives us our bond order of 4, 5, 6, 7, 8 minus 2 is 6 divided by 2 is 3. So the bond order here is 3. If we add an electron, where is it going? It's going into an anti-bonding orbital. So that will reduce the bond order by a half, right? Well, let's just calculate it. 2, let's see, 4, 8, and minus 3 is 5. So 5 halves equals 2.5, right? If we put another one out, let's see. If we put another one out here, that's 2. Now we're 4 divided by 2 is 2. Right? So that's 4, 5, 6, 7, 8. 8 minus 4 is 4, 2. Yeah, that's right. Bond order of 2. Now, if we start subtracting, we're starting from here, and we're subtracting 1. We're subtracting 1 from a bonding orbital. Right? So now we have 4, 5, 6, 7 minus 2 is 5 halves. We're back to 2.5. And if you subtract 2 of them, we're back to 4 minus 2, which is 2. So the moral of this story is the highest bond association energy is the one with the highest bond order in 2. And no matter what we do to this molecule, at least in this scenario, we're reducing the bond order. If we add electrons, they're going into anti-bonding orbitals. If we subtract electrons, they're going away from bonding orbitals. So it's the net same effect. 47. I like this rag better. This is the one I used for my WD-40 wipe. So it's already impregnated. It takes that stuff off real nice. Okay, which of the following molecules or ions does not contain a central atom? Is that? Oh, it slid off the side of the page. Hold on a second. That's why. D2sp3 hybridized, which is not D2sp3 hybridized. Okay. So A, B, C, D, and E. A is xenon pentafluoride ion. Okay. And ion tetrafluoride, iodine tetrafluoride anion, sulfur hexafluoride, and selenium pentafluoride anion. All these contain the central atom with D2sp3 hybridization. They all had that. Okay, so let's, this is 8. I want to count up electrons first. And 5 times 7 is 35, minus 1 for that charge. Okay, so that's 742. Yeah. And this is 5 times 7 is 35, plus 1 is 36 electrons. And sulfur is 6. 6 plus 6 times 7 is 42, is 48 electrons. And selenium is 6. Plus L.
5 times 7 is 35 plus 1. So that's 42. Yep, 42. So let's draw our structures. Xenon and then 5 fluorines. 2, 4, 6, 8, 10. So that's 32. 2, let's see, 6. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. And then 2 more goes here. So that's 1, 2, 3, 4, 5, 6 groups. That's D2sp3. Okay. Let's do this one. Iodine. Oh. There, that's correct. And then 4 fluorines. 2, 4, 6, 8. So that's 28. 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24, which means 4 electrons left. 2 here, 2 here. 2, 4, see, 1, 2, 3, 4, 5, 6 groups. That's D2sp3. SF6. 1, 2, 3, 4, 5, 6. Two, 4, 6, 8, 10, 12, which would be 36. 2, 4, 6 times 6 is 36. So an octet around each one of the fluorines uses up all the electrons. And that's D2sp3. 6 groups. And then the last one, selenium in the middle. 1, 2, 3, 4, 5. Okay. Oh, I forgot the chart. There. And 2, 4, 6, 8, 10. That's now we have 32. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. And you have 2 left over. Goes on the selenium. That's 6 groups. That's D2sp3. They're all D2sp3.
Professor Glenn,
Uh-huh.
in our paper, the SEF5, ours says SEF6. We have 48 electrons instead, we are 42. Still says the same answer, it looks like, but
Okay. Let's see, your review document number.
yeah, our review document says it's SEF6 instead of SEF5.
Okay. Yeah, you have the same outcome, don't you?
Yeah.
Mhm. Yeah, it
Just give one more.
6 of 1. Yeah, because if you take away a fluorine and you add an electron back for the missing bond, then it has to go into a lone pair. And with sulfur and selenium in the same, they're all chalcogens. This is going to happen whether it's, well, oxygen wouldn't work because it doesn't have period 3 d orbitals available. But for selenium, sulfur, selenium, tellurium, polonium, they would all work same way. Yeah. Whether it was 6 actual bonds or 5 plus a lone pair. Yeah. Okay, 47. Okay, we got some fill in the blanks, and those no big deal. Lots of repetition here. Here we go. Let's fill out this chart. Number 60. Okay. So we have molecules A, B, and C.
Molecules A, B, and C. And we're gonna designate C. 4 conditions. Okay. So the first one is electronic geometry. Then hybridization. And then bond angles. And examples. Okay. We're given molecule A is sp3 hybridized. Now we can look at what else is given. With A having sp3 hybridization, molecule B has 2 more effective pairs around the central atom than A. If it has 2 more pairs, then it has to be D2sp3. Right? Because you've got to have 2 more places to put those pairs. Molecule C consists of 1 sigma bond and 2 pi bonds. How can you have 1 sigma and 2 pi's? That can only happen with a diatomic molecule. Because if you have triatomics, then you got 2 sigmas, right? If you have any more than just 2 atoms, you have more than 1 sigma. So this has to be like this with you 2 pi's like that. It's a triple bond. So that means it has to be sp hybridized. Okay. Now the electronic geometry, this is going to be tetrahedral. This is going to be octahedral. This is going to be linear. 6 means octahedral, 4 means tetrahedral, 2 means linear.
On our review, or on our paper, we have molecular structure instead of your.
Oh,
Geometry.
you have molecular?
Yeah,
Okay, let me think. Electron pairs, effective pairs. Okay, is that worded differently? 60. It would have to be worded differently in order to be unambiguous. Yeah, molecular structure. Electron pairs. 2 more effective pairs. All right. We should say 2 bonding pairs around the central atom.
Oh.
Yeah, that would be that would eliminate the possibility for ambiguity between electronic and versus molecular. Because just one of them could be a lone pair, right? And that would change the molecular geometry. So let's see, bond angles for sp3. Nominally, they're 109.5 degrees. D2sp3, I always have to draw an octahedron for this one. We have X in the middle, and then we have like that, like that. So if we put something here, 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 if these positions are all filled, then we have the possibility for 90 degrees there, 90 degrees here, and 180 there. So we have 90 possible and 180 possible. And then for this one, there's only one possibility, 180 degrees. So what are good examples? Well, methane's a good one. Carbon tetrachloride is a good one. Either one of those would be tetrahedral. Now, if we're only electronic geometry, ammonia would work. But then it wouldn't have the tetrahedral molecular geometry. It would be a trigonal pyramid. Octahedral. Well, let's see. We need 6 bonding pairs. So we could do SF6. That would work. Or xenon. Hexafluoride. I think that would work. Let me see, would that work? That's not one of the possibilities there. This would be 8, 2, it'd be 50. Two, 4, 6, 8, 10, 12 would be 38. No, that's not going to work. So that's not a good example. SF6 is a good, it's a safe one. And this one, linear, well, it could be anything. It could be dinitrogen, or it could be carbon monoxide. That would work. Both of those have triple bonds. If we substitute molecular here. Okay. Let's see. And this, I think this is the last one. 61. All right. The order of molecular bonds is given for, I think, for N2 and O2. No, that's not given, is it? No, because this is the answer sheet. Okay, so that's a blank. And the question is asking you to fill out the molecular orbital setup. So notice that the only difference between the two is nitrogen has mixing. All right, so you have pi 2p first, and oxygen has no mixing, sigma 2p is first. So if you draw them like that, then you're safe. And then you count up the number of, this is only valence, the valence shells, the valence molecular orbitals. And then put in the valence electrons, and that gives you the structure. Then the question is, after you draw those orbital diagrams, explain why the removal of one electron in oxygen strengthens the bond, while the removal in dinitrogen weakens the bond. And it's fairly simple. If you move one from oxygen, it's coming out of an anti-bonding orbital. If you remove one from nitrogen, it's coming out of a bonding orbital. And that oxygen, it increases the bond order, decreases the bond order for nitrogen. Then you can put that in your own words. That's it. That's all I had marked. Scroll all the way back to the top. My document has a combined version 1 and 2. In case I want to talk about ones. But I don't think I did this time. Okay. Let's see. Did anybody else show up? Let's see. Nope. Nobody new showed up. Okay. So that's all I had to cover today. And we'll have an exam on this on Thursday, which is the only thing we're going to do. So if you need to have it, have the exam in bright space, let me know so I can open it up for you. And that's it. Till next week. Next week we'll do a final exam review. Okay. I don't have a special review document for the final exam. We're just gonna take the chapter review documents and we'll run through them. I think I have. Let's see. I'm gonna stop the share.